In a previous set of notes, I talked about the true confidence level for particular confidence intervals. In particular, we were talking about the walled confidence interval, and while I might state it is a 95% confidence interval, the actual true confidence level can be much, much less than that. And so the purpose of this next set of notes is to explore this a little bit further to help you understand what true confidence level means, and then we'll also take a look at how we can actually calculate it. So what we have here to begin with are 4 plots examining the performance of 4 different confidence intervals relative to their true confidence level. Now in each of these plots, and I should have mentioned this, alpha is 0.05, so our goal is a 95% confidence interval. I'm going to be looking at a situation where I have a number of trials of 40. So if I page down here, on the y-axis you see the true confidence level as stated. On the x-axis I have a particular value of pi. The true confidence level is what's plotted in the solid line. So for example, if we take a look at this dot dash line here, relative to the x-axis for the walled interval is drawn at pi is equal to 0.157. And if I project up to where I hit the solid line and then go over to the left to the y-axis, I get 0.8759 right here. And so what this says is if pi is 0.157 with n equal 40, alpha is 0.05, the 95% confidence interval, walled confidence interval that is, has a true confidence level of only about 88%. This is a lot less than what we would expect. This is why then this walled confidence interval is not something necessarily desirable to use. And so if we continue looking at this walled plot, what we can see is that, again, the goal is to get 95%, so this dotted line there. And we can see that the true confidence level for a walled interval rarely is 95%. The vast majority of the time for particular values of pi, it's actually much lower than that. That's why this interval should not be used in practice in most cases. Now, if we take a look at the Agresti-Cool interval, what we can see is that, again, we're not necessarily achieving exactly 95% for the true confidence level, or 0.95 for the true confidence level, but we're often very close to it. In particular, if I'm between 0.2 and 0.8, I'm fairly satisfied that my true confidence level is pretty close to 0.95. If I'm, let's say, more extreme, closer to 0 or closer to 1 for pi, we can see then the confidence interval becomes conservative, meaning that the true confidence level is above the stated level of 0.95 most of the time. The Wilson interval is very similar to the Agresti-Cool in its performance, except for very extreme values of pi, it can become a liberal interval, meaning that the true confidence level is less than the stated value. And so in case I don't think I said this, but if we look at the walled interval once again, with the true confidence level typically always being below 0.95 or 95%, that's why this interval is referred to as a liberal interval. We'll talk more about the Clopper-Pearson later. So just to make sure that you fully understand, what does a true confidence level mean? Let's think of it in this manner. Suppose a random sample of size n equal 40 is taken from a population, and a 95% confidence interval is calculated for pi. Suppose another sample is taken, n equal 40 again, 95% confidence interval, walled confidence interval is calculated once more. And suppose I repeat this whole process 10,000 times. What the 95% confidence level is supposed to mean is that approximately 9,500 of these 10,000 different confidence intervals I'm calculating should contain the one true value of pi. Unfortunately, though, as what we saw from that plot when pi was 0.157 specifically, this doesn't happen. And in fact, the only time that this is ever guaranteed to happen is if you had a sample size of infinity, and unfortunately you're never going to have a sample size of infinity. And so the true confidence level then is in the percent of times that the confidence intervals do contain pi. Some people will refer to this as the confidence intervals cover pi. And so that's why often you will hear people refer to true confidence level as coverage level. Now this process that I just described to you, if I could actually program that into a computer, and basically when I do that, this is referred to as a Monte Carlo simulation. And we'll take a look at how to do that shortly. Now, the way that the true confidence levels are calculated on the plot on the previous page is slightly different than the way that I just described here, but in essence it's going to give you something very, very close. And we'll take a look at how those previous plots were actually calculated shortly as well. But for now, what you can think of how those plots were done is that imagine in R you set pi to be 0.0005. Then you take 10,000 samples. For each sample corresponding to this pi, calculate all 10,000 confidence intervals, and you look how often each of those confidence intervals contain 0.0005. So once you get that, then you plot a point on your plot at pi 0.0005 and the corresponding true confidence level that you just got. Then, let's say go to 0.0010. Do that exact same process. Get a point that you can then plot on that plot. In other words, match up the 0.0001 with the true confidence level that you calculate from your Monte Carlo simulation. And then repeat this process for all values of pi, all the way up to, let's say, maybe 0.9995 by 0.0005. That's a way you can think about how those calculations were done. And also let's take a look at the previous plot too. If I were to look at pi 0.157 here, and if I project up and then over, we can see for pi equal 0.157 for aggressive cool, the true confidence level is very close to 0.95. Same with the Wilson. In fact, the actual value ends up being 0.9507. Again, that's why the aggressive cool and the Wilson should be used over that walled confidence interval. Okay, so let's talk about some of these calculation details. So what we're going to be doing is calculating an estimated true confidence level for the walled interval. My corresponding code is in conflevel.r. The reason why I call it estimated is because I would need to do a Monte Carlo simulation with an infinite number of samples, and obviously I cannot do that. So what we're going to do is just take 1,000 samples rather than 10,000 that I described on the previous page, just to speed up the process. And let me go ahead and go over to 10 here. And what I'm going to do is set an alpha to be 0.05, set a pi to be 0.157, and my number of trials, you could say per sample, is going to be 40. So just verify, you can see indeed n is 40. If I move down in my program, you see where it says estimated true confidence level. What I'm going to do again is take 1,000 samples. And we've talked about how to take a sample before in this kind of a setting. What we basically need to do is observe a binomial random variable that has n equal 40, pi equal 0.157. We talked about how to do that. We use the rbinom function for that. I'm going to set a seed so that I can always reproduce my results. So let me go ahead and run this segment of code. And if I use, let's say, the head function with w, what that does, it gives me the first 6 values of what I came up with. And so for my first sample, I got 6 out of 40. I got 6 successes out of 40 trials. For my third, I got 7 out of 40, and so on. Now I can also, if I wanted to, summarize all these 1,000 different success counts in like a table-like structure using the function called table. So table, the first argument or main argument is x, and I'm going to say I want to summarize what's in W. Put the results into something called counts. And so we can see that 8 times out of 1,000 I got a 1. 172 times out of 1,000 I actually observed a 7 for my count. 7 successes out of 40 trials. Okay. Now for each of these 1,000 let's say W values, what I want to do is find the corresponding pi hat. So I say, as similar to what we've done before when we only had one sample, I take W divided by N. W again has 1,000 different values in it, and for each of them I'm going to divide by 40. And then if I look at the first 10 of those pi hats, I get 0.15 for the first one. That's simply 6 divided by 40. 0.175 for the third one. That's going to be 7 divided by 40. So I have 1,000 different pi hats now. Using each of these pi hats, then I want to find, let's say, a walled confidence interval. So what I can do is I can basically use exactly the same code that we've seen before, but now just understanding that I have 1,000 different pi hats here. So, for example, we see inside the var.walled equation 1 minus pi hat. So 1 is obviously just one numerical value. Pi hat has 1,000 different numerical values in it. And so the way that R is going to react to this is going to take 1 minus that first pi hat, 1 minus the second pi hat, and so on. Let's actually see that. Oops. And we can see that I got 1,000 of these 1 minus pi hats. Next, if I divide each of these by n, so unfortunately 10R is not working as well as I would like right now. Hold on a second. I take 1 minus pi hat divided by n. So now again I got 1,000 of these. And again, pi hat itself has 1,000 different elements as well. And so the way that R is going to react when it has something that has 1,000 values here, it has 1,000 values there, what's going to do is match each of them up so that the first pi hat times the first 1 minus pi hat divided by n. Then it goes to the second pi hat. It's going to match it up with the second value of 1 minus pi hat divided by n. And eventually we keep on doing that, put all the results into var.walled, and this is what we get right there. So if I do head var.walled, if I do head pi.hat, we can see if I did pi.hat, the first value, times 1 minus pi.hat, first value, divide by n, I get 0.003185, and that's exactly what's there. Okay. Then from there, I can find my lower limit and my upper limit for 1,000 different confidence intervals using this very same methods that we've talked about before. So let me go ahead and do that. So for example, the first 6 lower bounds, the first 6 upper bounds are right there. How about we put all this in a nice data frame to display it? So I'm going to put all my W's, all my pi hats, all my lower bounds, all my upper bounds, and since I have 1,000 of them, how about we just display the first 10 of them? Okay. So again, the way that R works here is that it recognizes that there's rows and columns in this data frame, and so if I say 1:10, what that says is take the numbers 1, 2, 3 all the way up to 10, and I only want to display those first rows or those first 10 rows because I'm in the row index there. I don't have any column index, so that gives me all the columns. And here we go. So for the very first sample, I have 6 successes. Pi hat's 0.15. My lower limit is about 0.039. My upper limit is 0.26 for my walled confidence interval. Remember, pi is 0.157. So did the confidence interval work? Does it contain 0.157? The answer is yes. Let's go down, though, to the 8th sample that we got out of these 1,000. I have 3 successes observed. pi hat's 0.075. Ooh, look at this lower bound. It's negative. Remember, that was one of the problems with these walled intervals. They can be outside the range of 0 to 1. So I have a negative 0.0066 as my lower bound. My upper bound is 0.1566. Notice 0.157, our value of pi, is not in the interval. So this confidence interval, you could say, did not work. It does not contain the true parameter value. Well, how often does this, well, when does this happen? How often does it happen? And so that's what this next set of code allows me to do. Remember, pi is 0.157. And what I can do is do a logical comparison. Is pi greater than the lower bound? I have 1,000 lower bounds, so what's going to happen is that R is going to return a bunch of trues and falses, 1,000 of them, to make that check for me. I could do exactly the same thing for the upper bound, but now is it less? Again, we want pi to be greater than the lower bound and less than the upper bound, because that means the confidence interval contains pi. And then if I were to put all these trues and falses together with the ampersand, which means and, I can look at, well, when did the confidence interval work? Okay, so the very last sampled value, it did. That's why I have a true. But the third to last one, it did not. So what I have here is a bunch of trues and falses that tells me, did the confidence interval work or not? Let me actually show you some of this as well. So here's the first 10 of these saves. The first sample, yes, it did work. And we saw that indeed 0.157 is in that interval. But take a look at number 8 again. 0.157 is not, so save should be false, and indeed it is. So how many times do I get a true? How many times do I get a false? How often do I get a true? And that's basically what the mean function can be used here for. So if I take the mean of save, you might be thinking, wait a second, how can you take an average value of trues and falses? R converts trues to ones, falses to zeros. And so if I do that, I get a value of 0.878. What this means is that out of the 1,000 different confidence intervals that I found, 878 contained pi. 122 did not. So the proportion of time that the confidence interval worked is 0.878. This is called my estimated true confidence level. Look at how close it actually ended up being to what I mentioned before was the actual true confidence level of 0.8759. Okay? Actually, let me just stay in my notes here. Okay, so that's how we can use Monte Carlo simulation to estimate a true confidence level. This is a very, very useful tool to have. Monte Carlo simulations are widely used in statistics to evaluate how good a statistical procedure is. In this particular case, we see this statistical procedure is not good because it's not doing what it's supposed to be doing, which is to have a true confidence level of 0.95. Now, to relate this to some stuff that we were looking at before, we saw previously for a walled interval that we had this particular probability statement. That, for a large sample, the probability that I have this lower bound, I have this upper bound, pi is in the middle of it, the probability that this statement works is approximately 1 minus alpha for a large sample size when using a normal distribution approximation, where we can think of pi hat here as a random variable. Well, what we just saw was when pi is 0.157 and alpha is 0.05, this approximation is not good. And so what Monte Carlo simulation then is trying to do for us to calculate this probability is what it's trying to do is estimating the probability W is equal to 0. It's estimating the probability W is equal to 1, all the way up to n equal 40. And it's using the probabilities associated with this to basically estimate then this corresponding probability. So to help explain this a little bit better, what we can do is as follows. Let me come back up here. So here's a table of counts corresponding to our simulation. So for example, 172 times, or in other words, 0.172 proportion of the time, we got a 7. 0.008 is the proportion of times that we got a 1. Now, I will tell you, and you'll see how this is done shortly, I will tell you that if I were to compute this wall confidence interval for W values of 1, 2, 3, all the way up to 13, I will tell you that when W is equal to 4 through 11, the confidence interval contains pi, 0.157. Otherwise, it does not. And so, what then this Monte Carlo simulation study is doing is basically, let me keep on writing here, it's going to add up all these proportions of observing 4 through 11, and that is how this probability is estimated. So let's take a look at that a little bit more closely. Let me come back over here to 10. Okay. So we have our sample in W. We have 1,000 different values there. Counts contains then the number of times you observe a 1, a 2, and so on. And if I put then the proportion of times into an object called prop.w, we'll get these proportions that I was writing on my Word document. And what we could do is that since I know I have values from 1 to 13, how about we actually look at then the corresponding probability associated with the binomial distribution for this particular pi. So we've seen that before. We can use the d binom function for that. And so let me go ahead and do that. And we have these probabilities. And so what ends up happening, and we saw this before when we were simulating data like this, is that this 0.008 from my sample is basically estimating 0.008 from actually using the probability distribution. And we get what we expect. Let's see now, for W equals 7, 17.2% of the time, or 0.172 proportion of the time, we had a 7. And if I count 1, 2, 3, 4, 5, 6, 7, but in actuality, the probability is 0.1564, but still, it's pretty close. And so what Monte Carlo simulation is doing is basically taking these using estimated probabilities to estimate these true probabilities there. And so we can take a look at that a little bit more closely in this particular table. And so, what I was saying to you before is that if I were to sum up all those proportions corresponding to when the confidence interval contains pi equal 0.157. Again, you'll see shortly when that does happen, but for now, believe me, it is between W is equal to 4 to 11. If I were to sum up those proportions where you see my mouse, that's how I get to 0.878. And hopefully right now you're probably wondering, well, if I can sum up those proportions, why don't I just use the actual true probabilities that we know? You could do that. And in fact, that's how those previous plots on the first page came up. The actual probabilities from the binomial distribution were summed. Okay, one little quick note here before I move on. You might remember me making this small change to the code here. Basically what I do in this obs.w is I use a little bit more fancier ways that I can pull out what the observed values of W were And, I'm not going to go into details. You can execute the code on your own to see that that indeed truly does happen. Okay. Let me come back over here to my notes. Okay. So then, to find the actual true confidence level without having using Monte Carlo simulation, here's how we can do it. How about we just simply find all possible intervals that one could calculate with w equals 0, 1, all the way up to n. And then we need to form what's called an indicator variable to indicate to us, does the interval contain pi equal 0.157 or not? And so in math, in stats, we typically indicate an indicator variable with I of w, meaning that this I is for indicates, and we can see it's a function of what w is. So I of w is equal to 1 if the interval for a w contains pi, 0 otherwise. And then to calculate the true confidence level, what we do is we take the binomial distribution. We saw all those binomial probabilities already calculated, and we multiply it by a 1 or 0 corresponding to if at that w, pi is inside the interval. And then we sum up then the resulting probabilities that come about through this. So this is a non-simulation based way to do these, to find this true confidence level or this coverage level. For those of you who have more experience beyond this class in terms of using Monte Carlo simulation, you might be thinking, well, wait a second, I've never seen something like this before. I've only done this through Monte Carlo simulation. And the reason why we can do it this way is because we have a finite number of possible values of w. So there you go. I guess also a little bit of a side note too. I expect that there are probably some people who are watching this video who are or taking my class who have not done Monte Carlo simulation before. First of all, again, please remember to think of my code as a template. So maybe instead of using n equal 40, I might ask you in the future to use n equal 100. Well, wherever you see n, make a change to 100. Also, while Monte Carlo simulation is becoming more prevalently used in introduction to statistics courses, the prerequisite for this course, and in fact, I always use Monte Carlo simulation whenever I teach one of those courses. I do understand that sometimes a professor will not do that. And so if you needed a little bit more help to understand Monte Carlo simulation, I can point you to where in my introductory statistics course website where I actually introduce Monte Carlo simulation in the context of a confidence interval for a population mean, and that might help you understand this better too. Okay, so let's take a look at some R code so that we can actually calculate the actual true confidence level here for a walled interval. And let me come back over here to my program once again. So again, I need all possible values of w. So I'm going to let w get 0 to, as in T-O-N. So just to show you what that looks like. There we go. I'm going to have all my different pi hat values as well. Do that. So take each of those w's, divide by n. Then I want to find probabilities associated with each of those w values. So again, I use the d binom function to allow me to do that. Next, I need to find all my variances associated with pi hat. And then I find the lower bound and the upper bound for all these pi hats as well. Using these pi hats, find the lower and upper bound for the interval. So let me go ahead and do that. And so we can see here's the lower bounds, here's the upper bounds. So again, what this means is that there's only 41 possible intervals that one could ever have if n was equal to 40. And then next, what I like to be able to do is check, is pi above the lower bound? Is it below the upper bound? If it is, the interval contains pi. If not, it does not. So I put that into save. And so we have all these falses and trues as well. And then next, what I want to do is basically what is shown in this equation here. Okay. I want to add all those binomial probabilities that correspond to when the interval contains pi. And so what I'm going to do is I'm going to create my save vector in my program. Essentially is my indicator function. I'm going to take save, which has 41 different values, times each of the corresponding 41 probability values from the binomial. When I do that, then the ones then allow me to keep those corresponding binomial probability values, and I can simply sum them up to find the true confidence level. So let's go ahead and take a look at that. So I take the save times the PMF, and there's my true confidence level, 0.8759. And to help explain this a little bit better, let's look at a data frame representation of what's going on. So we can see, for example, when W is equal to 3, pi hat is 0.075. The probability of observing W equal to 3 is 0.0689. Here's the lower bound of the interval. Here's the upper bound of the interval. Notice it does not contain pi equal 0.157, so that's why I have a false there. But when W becomes 4, my confidence interval is now 0.007 to 0.193. Yes, indeed, that does contain 0.157. And so what I'm going to do here is simply add up all the values in the PMF column, and that's my actual true confidence level. Okay. Now, this is for only one pi. What if I want to actually reproduce the plot that we saw at the very beginning of the notes? Well, what I need to do is the exact same process now, let's say maybe for 0.0005 for pi, all the way up to 0.9995 by some fine interval, such as by 0.0005 as well. How can I do that then? Well, I could rerun the code a whole bunch of different times or put it all into a for loop. And so let's take a look at that. My corresponding code is conf levels walled only.r. Okay. So I do the exact same calculations that we saw before. I need to find all those corresponding confidence intervals. Again, there's going to be 41 different ones because n is equal to 40. Then I'm going to create a new object called pi.seq for sequence. I need to find a sequence of these pi values. I want to go, for some reason I went from 0.001 instead of 0.0005. And so I'm just getting a sequence of values from a small value of pi to a large value of pi, going pi 0.005. For now, let's make things a little bit easier. We're going to use this commented set of code instead. We're going to go from 0.1 to 0.9 by 0.1. So to show you what that looks like, there we go. So I have just 9 different values of pi. Then for each of these pi's, I want to find the true confidence level. And I'm going to do that, but I need a place to store all the results. So I'm going to create an object called save.true.conf, for the lack of a better name. And it's going to get a value that comes from the function called matrix. A matrix is basically a set of rows and columns that allows you to store information. And so what I'm going to use this as a storage device, where I'm going to initialize each value in that matrix with NA for not available yet. The number of rows in the matrix is going to be the length of pi.sq. In other words, 9. It's the number of values of pi that I'm looking at initially. And I'm going to have 2 columns because I'm going to put pi in the first column and then the actual true confidence level in the second column. So let me go ahead and run that to help explain what that looks like. And there you go. So again, this is just a storage device where I'm going to put the results in. Now I'm going to, with this looping structure that I'm going to have, I need to somehow count which row I'm talking about. Like row 1, row 2, row 3, and I'm going to initialize this as row 1. So I just have an object I call counter for the lack of a better name as well. Okay, so now let's take a look at a for loop. A for loop is a very common device that's used whenever you're doing computer programming that allows you to repeat a process over and over and over again. In this particular case for R, the way that the syntax for a for loop is to say for and then parentheses, because this is actual function. You can say pi, again I'm interested in different values of pi, in my pi.sequence. End parentheses, left curly bracket. And notice I have a right curly bracket as well. And so what that means is in this for loop, the code that I just highlighted is going to be repeated for pi equal 0.001. I'm sorry, pi is going to be, this code is going to be repeated for pi equal 0.1, pi equal 0.2, all the way up to pi equal to 0.9. So to help us see this and to help understand how a for loop works, if you haven't seen it before, I'm going to put some statements in here that allows me to print the value of pi. Also, it's going to allow me to print where I end up storing the results. So inside this for loop, what I'm going to do is calculate the corresponding probabilities with a particular value of pi. So again, the first time through it's going to be pi equal 0.1. Then similar to what we saw before, I'm going to check, is pi greater than the lower bound? Is pi less than the lower bound? So here's where I calculated the lower and upper bound. Again, there's only going to be 41 different possible values. Put the results into something called save.wald. And then just like how I was calculating the true confidence level before, I take the sum of these, what will end up being zeros and ones, the falses and the trues, times the corresponding probability. I sum them up. I put the results into wald. Okay. Now this is when I want to save the results. So I'm going to combine together my pi and the corresponding true confidence level. I'm going to put that into my matrix here, corresponding to the row number of counter. Then I reinitialize my counter so that I can do now repeat this for row 2, and then eventually for row 3 and row 4 and so on. So let's go ahead and execute this. And so what ends up happening is that here's the first time through the loop. And this is what came about through using the print function. The first time pi is 0.1. Then I put the results of 0.1 and a true confidence level of 9144 into my matrix. Next time through the loop, pi is 0.2. I put in a value of 0.904678 as my true confidence level. And I keep on going here. Let me actually rerun this now for the whole sequence of the pi's. I'm going to turn off the printing so we don't see it. Okay, yeah, let me just restart that. Okay, obviously I'm doing something wrong here. Let me see if I can figure it out real quick. Actually, sometimes it's just better to, yeah, I know what I did wrong. Rerun the entire code first, and there we go. So what we have here, let me do a head on save.true.conf. What we have here is all the values of pi in the first column, all the true confidence levels, actual true confidence levels in the second column. So notice when pi is 0.001, the true confidence level is only 0.03. Remember, this is supposed to be for a 95% confidence interval, so you can see how off we are. If I use, let's say, the tail function in R, I can see the last 6 by default, and we see something very similar. Okay, so let's do a plot. Let's actually essentially reproduce the walled part of that first plot on page 1. And so to do that, I'm going to open up a new plotting window. Let me go ahead and run that. And open up in a different monitor that I have going on right now. And then I'm going to plot all the values of pi, because they were in the first column on my x-axis, all the values of the true confidence levels, that was in the second column. Put a nice title on the plot, x-axis label. I'm going to put the Greek letter pi on the x-axis, so that's what expression allows me to do. Y-axis label, and then I want a line plot. I don't want to see individual points for each of the different values of pi and the true confidence level, so I want to connect them with a line, so that's why I'm going to do type equal quote L end quote. And then just so that it's easier to read, I'm going to limit the y-axis to be between 0.85 and 1. Lastly, I'm going to put a horizontal line, that's what H stands for, a horizontal line at 1 minus alpha, which will be 0.95. It's going to be a dotted line. I can do this using the AB line function. So let me go ahead and run this segment of code. And now we have the exact same plot that we saw on page 1. Okay. Again, there's a lot of code here, but think of this as a template for your own code. Execute small portions of it as well so that you can see what the code is doing, so you can learn how to do all this stuff properly in R. Now, one thing you might be interested in is, well, or you might be asking is, well, why do we see this oscillation of the true confidence levels? You know, let me actually go back to my notes here. And let me make this a little bit bigger. So we can see again at pi equal 0.157, my true confidence level is 0.8759. But if I were to move, let's say, to pi equal 0.156 and project up, what will end up happening, we have a true confidence level that's much, much, much closer to 0.95. Well, why does that occur? Well, it ends up occurring because of the discreteness of the binomial distribution. Let me show you a nice little table that helps explain that. Okay. So here's what we saw previously in R. We have all the different values of W. We have the corresponding lower and upper bounds. And then we have the save here, which indicates does that confidence interval contain 0.157 or not. And so if I draw a straight line, if I can, over, again, for W equal to 4 through 11, the confidence interval does contain 0.157. But we notice here it's just barely off for W equal 3. So if pi, though, was 0.156 instead, look what happens. Now this will become true. And so now we're going to, in our calculation, include all of these probabilities. So that new probability is 0.6089 that we've included. And that is the difference in right here and right here relative to that y-axis. So that's why that oscillation occurs. The discreteness of the binomial distribution causes these jumps to happen in the true confidence levels. Okay, so let's move on. We got one more confidence interval that I want to discuss. It's called the Clopper-Pearson interval. I briefly mentioned this before. And the reason why we want to discuss this is because right now you might be thinking, well, wait a second. I can see that the Wald confidence interval doesn't work very well, but Agresti, Kuhl, and Wilson, they're not exactly 0.95. Wouldn't you want to be exact? Or at the very least, wouldn't you want to be at least 0.95, meaning being over or higher than 0.95, so that you have a conservative interval? Because that seems like that would be a better thing to be conservative rather than liberal at times. Some people feel that way. And so what the Clopper-Pearson interval does, it allows you to be conservative. It is guaranteed to have a true confidence level of at least 1 minus alpha times 100%. In other words, if you have alpha 0.05, at least 95%. The lower and the upper limit for this confidence interval is based upon a quantile from the beta distribution. And at least for those who only have an introductory stat course before coming into this video, Most likely you've not seen a beta distribution before. So let's talk about what the beta distribution is, how we're going to use it, and then the corresponding R code to calculate the interval. So beta probability distribution is just another probability distribution. Some characteristics about it is that if I have a random variable, we'll call it V, possible values of this beta distribution can only be between 0 and 1 in terms of the actual random variable itself. It has two parameters. They have to be positive. We'll call these parameters A and B. And so then the probability distribution, or more formally the probability density function, looks like this. We have V raised to the A minus 1 power. We have 1 minus V raised to the B minus 1 power. And then we have this constant out in front that's dependent upon what's called a gamma function. A gamma function is just a mathematical function where if I had, let's say, gamma of C, where C was an integer, this would be C minus 1 factorial. If C is not an integer, then we have to use some integration to find out what that value is. Okay. We have functions in R that will automatically calculate values from this probability distribution for us. So this is essentially the last time that we'll see this particular equation. No, second to last time. Because we need to see it again when we talk about a quantile from that distribution. So let's say here's a plot of a beta distribution. There's many different shapes of a beta distribution. This is one possible one. Let's say I want to find a particular quantile right here, such that the area to the left of it is maybe like alpha. Then I can, if I were to use calculus for this, set alpha is equal to the integral from 0 to what that quantile is, we'll call it V sub alpha, and integrate my density function relative to V. This gives me my probability, or that area underneath the curve. If you're not comfortable with the calculus explanation, just think of it as the area underneath the curve that's to the left of your quantile of interest. We can denote the quantile as V sub alpha, or what we will mostly do is call it beta of alpha, and then we make sure to put the two parameters there because that controls the shape of the probability distribution. If you want to see what the shape of the probability distribution is, I have a program called beta.r that allows you to interactively investigate that. Here are 4 different possible plots from this particular program for different beta distributions. And what you can see for the different beta distributions, where the first value is A, the second value is B, you can see it has a wide variety of shapes. And so finally, then we can get to the statement of what the Clopper-Pearson confidence interval is. Simply, it's the alpha divided by 2 quantile from a particular beta distribution. That's the lower bound, where we have the number of successes as the A parameter. We have the number of failures plus 1 as the B parameter. Then for the upper bound, we take the 1 minus alpha divided by 2 quantile, where we have the number of successes plus 1 is the A parameter. The number of failures is the B parameter. Where does this interval come from? In this particular class, we don't go through that kind of a derivation. If you've had a mathematical statistics course, you're welcome to take a look at a mathematical statistics book where typically one shows this kind of a derivation that relies on a relationship between the binomial distribution and the beta distribution. So for example, a classic mathematical statistics book is one by Cassell and Berger, and it's actually part of an exercise in that book to show this relationship. Now we do have a little bit of a problem. If W is equal to 0, notice what happens. A is equal to 0. But I just told you for that probability distribution, A has to be greater than 0. So what can we do? Well, just take the lower bound for the interval to be 0. A similar thing happens if W is equal to N. We have a problem right here. And so just take the upper bound to be 1 in that situation. There may be a few of you who have seen the Clopper-Pearson interval before, and if that is the case, you might have seen it stated a little bit differently. It uses the F distribution. In the end, you get exactly the same lower and upper limits. It just uses a mathematical statistics relationship between the beta and the F to show it a different way. We'll just stick with the beta distribution. So as I said, is that the Clopper-Pearson will always have a true confidence level that's greater than or equal to 1 minus alpha. That is the strength of this interval. And you might be thinking, well, why don't we just use that all the time then? Why don't we just use this interval? The problem is, for this case and other intervals like this that has this guarantee, is that they tend to be wider than other intervals. That wideness is why it can get this guarantee. Now, with confidence intervals in general, as you would learn in an intro stat course, you know we want this interval to be as narrow as possible, but still to have that true confidence level about 0.95 or 1 minus alpha times 100% to be more general. And so that's why people will often use those other intervals, the Wilson and Agresti-Cool, when they don't have to or they don't necessarily need to have that guarantee. So since we do have that guarantee, then this is referred to as a conservative interval. Okay, let's look at the plot just to show you. So here's the Clopper-Pearson plot from the first page, and we can see that indeed the true confidence level is always above 0.95 there. Sometimes a lot above 0.95. Okay, so let's talk about how we can calculate this in R. Well, we need two quantiles from a beta distribution. Similar to what you've seen like for a normal distribution or a chi-square distribution, there happens to be a function in R that automatically calculates the quantile from that probability distribution. It's called Q beta, quantile beta. The first argument is P. That represents the probability you are to the left of the quantile. The A parameter is what R calls shape 1. The B parameter is what R calls shape 2. So this is how you get the upper bound, the lower bound, and then the upper bound is found in a similar way. You just always got to change these shape 1 and shape 2 values corresponding to what was in the previously in the notes. And so if I do the calculation, put the results into a nice data frame, there you see the interval 0.12 to 0.74 approximately. One could combine the lower and the upper code here to one line of code by taking advantage of how R does its calculations based upon vectors of values. And so this is what I do here to get exactly the same thing. We saw the binom package earlier in another set of notes. This package also calculates the Clopper-Pearson interval. And so what one could do is use methods equal all, and you'll see it listed as exact. If you just specify methods equal exact, you get then the corresponding interval. Now, why is exact used rather than Clopper-Pearson? The reason being is because this is referred to as a form of exact inference in statistics, because we're using the exact probability distribution, the binomial and its relationship with the beta, to calculate the interval. The word exact, though, does not mean that this true confidence level is exactly 0.95. And we saw that from the plot. The word exact corresponds to the probability distribution that's being used. Lastly, here's a summary of all those intervals that we've calculated. And we can see for the Clopper-Pearson, it is definitely wider than the Wilson and the Agresti-Cool. That is the side effect of using one of these intervals. This type of a way to find an interval is to get that guarantee, we need to have a wider interval than what we might get if we use one of those other ones. Okay, so then this concludes then this section about true confidence levels and also the Clopper-Pearson interval. Again, there's a large set of code with those true confidence level calculations, and so you do need to ask questions if you have them with regards to those those programs and the corresponding code. So that concludes in this section.